Okay, ladies and gentlemen, this is going to be a bit of a mathematical, very glancing overview, but I think a somewhat scientifically minded analysis of the compression readings that should be attained in a just standard Toyota 22R, 22RE, particularly the naturally aspirated engines, because I haven't gotten into the fluid dynamics behind the flow of compressed gases, especially under a turbocharger. You know, you run 10 or 15 pounds of boost. I know that's not what a stock R8 turbo runs, but I don't wish to get into those kind of compression readings, especially when one goes into boost. Anyhow, this was just a set of compression readings that I took, yesterday? Christmas Day? Yeah, I took these Christmas Day using my Carlisle compression tester. And I'm not going to speak to the veracity of this first set of compression readings. Might have had a loose O-ring. I'm thinking especially on that second cylinder. This is going, of course, front to back. But it appears as though the rings in the engine are worn out. Interestingly enough, when I did the compression test last year, I got 120 pounds per square inch across the board. There was maybe 5 pounds per square inch variation between all the cylinders, so that was good. I think the only variation really was on this cylinder, so it wouldn't surprise me if I'd achieved 115. These tests were taken as about 25 degrees Fahrenheit outside, which leads me into the next sort of concept. We have the ideal gas law. Pressure in pounds per square inch, atmospheres, whatever, doesn't really matter. For this one, I was using atmospheres, which is how we always did it in my chemistry class, times volume in liters is equal to N, your number of moles of a gas occupying a volume, times R, which is, I think, joules per atmosphere degrees centigrade or something like that. It's some stupid constant, but it's 8.314 times temperature in degrees centigrade. Or in degrees Kelvin, rather. Now, you'll notice that you can isolate that R to get PV over NT is equal to that R constant always. And since it's always equal to that R constant, and if you have a sealed container where you know that your temperature and your number of moles aren't changing, you can set your pressure and volumes under different circumstances equal to each other. So you change the pressure, but the volume remains the same. You can use that to solve for your second pressure. Likewise, if you change the volume, say, have a cylinder go up in its bore, you can change your pressure and solve for that. P1 V1 is equal to P2 V2. I think that's the only equation I'm going to need, but that is really going based off of a set of assumptions about the actual volume of the cylinder and combustion chamber, right? Because that combustion chamber, I think, is roughly hemispherical in design, 2 valve per cylinder, but I think it's a hemispherical swirl type combustion chamber. I was reading online anywhere between 57 and 84 cubic centimeters of combustion chamber volume. Of course, with an 89 millimeter stroke and a 92 millimeter bore. Stroke is the height of the cylinder, and the bore, 1/2 of the bore, is the radius, which leads us into our equation up here. The volume of a cylinder is equal to pi multiplied by the radius squared, so 1/2 of that diameter, 1/2 of that bore measurement times the height, which is the stroke. That'll give you the volume of your cylinder. Interestingly enough, if you wanted to find the volume of the combustion chamber, assuming that the piston A had a flat top, which, again, this is where I'm making some assumptions, but assuming that piston has a flat top, that the space between the rings and the top of the piston does not account for any volume, and that the top of that piston sits flush with the top of the cylinder deck. The only thing then that we would be measuring is the actual volume of the combustion chamber itself, which I know is not the case in this engine. I think it has a set of domed pistons in it from Toyota, from the factory. If not, it might have dish pistons in it if somebody's ever been through it. That being said, I plugged in over here a set of numbers and multiplied that out, but I'll get to that in a second, combustion chamber volume. I did want to preface this by saying the Toyota factory service manual you got that off eBay? Anyhow, that Toyota factory service manual expects you to have 142 pounds per square inch of compression to 171 pounds per square inch. Now, let me just do a quick calculation here. 142 over 171 is equal to, so they're expecting that your values, your lowest value is 83% of your highest value, right? So even though your compression numbers may not all look this good, if they're all above 100 and you're below, say, I don't know, 7,000 feet above sea level, which is 99% of the world population, and your compression results are all within 5 to 10% of each other, at the very most 15% variation, right? But you really do want them 5 to 10% of each other. Then you know that the health of the rings is consistent across the board. The health of the valve train is likewise across the board pretty stable. That's why they give you a range. You want to kind of have a mean value, and you don't want a great percentage variation from that on any of the cylinders. Now, given these compression readings, you know, this is pressure 1 times volume 1. I figure if you change that initial pressure, P1 over here to be 0.821 atmospheres, which is up here, 0.821 atmospheres. So if you change that P1 and you leave your V1 the same, then you can probably, oh, interesting. V2. Okay, I might have to come back to that. This is rather interesting to me. I did a little bit of thinking about this, but say that you plug these numbers in into the original P1, V1, P2, V2 equation, right? So I just did that briefly over here. I converted 142 pounds per square inch to atmospheres by dividing that by 14.96 atmospheres per, or 14.69 pounds per square inch per 1 atmosphere. And that yielded 9.66 atmospheres, which I could then divide from V2 and could divide by that amount to get a combustion chamber volume of 50.2 centimeters cubed. And likewise, when I plugged 171 in, it's giving me a volume of 41.7 centimeters cubed. So I really do think that this has something to do with sort of averages then, and the shape of pistons and the kind of volume that's being displaced internally. You'll also notice that the way that compression readings tend to go, if you do 10 or 15 revolutions of the motor, is you get an initial reading on a gas engine of like 80, 100, 105, 110, 112, 115. At 1, 2, 3, 4, 5, you know, on your 6th stroke, you might get the highest reading. But you'll notice that it very rapidly tapers off until you get the sort of highest reading. So I bet you that has something to do with it. But again, I have no way of verifying that, no mathematical equations. That being said, the Toyota owner's manual, or whatever that is, Toyota truck manual, says somewhere in there, the displacement of the engine is 2,366 cubic centimeters. It's somewhere in here. Anyhow, I don't think that's hugely important, but it is 2,366 cubic centimeters. If you divide that by 4, because it's an even displacement 4-cylinder engine, you should get about 591.5 centimeters cubed per cylinder. Now this is where it got interesting. I divided 57 centimeters cubed. I plugged it in as 0.057 and divided that by 0.591 because that is how many cubic liters it is. It's 57 1,000ths of a liter, which is kind of a weird way to think about it. But that gave a compression ratio of 10.4 to 1, which is way higher than what the Toyota manual ever specified, even for a 22RE. For a 9.4 to 1, so I did 1 divided by 9.4 and then multiplied that by 0.591 liters to get 0.0629 liters, or 62.9 centimeters cubed. I have the sneaking suspicion this is somewhere near the actual amount of volume in the combustion chamber whenever the piston's at top dead center with the valves closed. And then this is the 9.0 to 1 value that I was using again for that same 591 centimeter cubed. Here are barometric pressure readings at the airport on the 25th of December, about 3 p.m. yesterday, and how many atmospheres are present at the university, which is maybe 100 feet higher than where I am here, so it's fairly accurate. Anyhow, here's the actual math of what I did. Sorry to sort of beat around the bush. Oh yeah, you can see 1.4 is 62 point, and then 1/9 yielded that. So I set up all of my pressure 1, volume 1, pressure 2, volume 2 equations. Now, interestingly enough, when I plugged in that 1/9 of the initial displacement, I got a value of 7.385 atmosphere, or 108.5 pounds per square inch, which isn't terribly out of line with, some of the values that I was seeing here, but that's really not a great compression number. Up here, more along the lines of what I was expecting, and kind of the lines of what I'd seen last time, was this 125 pounds per square inch value, somewhere around there, somewhere between 120 and 130. And I got that using the 0.057 liters, or the 57 cubic centimeter combustion chamber volume, which I thought was a little bit interesting. I did the same down here, 57 centimeters cubed at sea level, right? I plugged in 1 atmosphere, 14.9 pounds per square inch. You can just make the conversion over here if you so choose, whatever. But again, 10.368 atmospheres, you multiply 10 by 14.96, you're going to get somewhere around 149, and indeed we did. Got about 152 pounds per square inch. Pardon, I didn't write the units. Take numbers off of my test. And then, of course, last but not least, we plugged the 0.65 value in there. About 9 atmospheres, or 132 psi, which again you'll notice is lower than the specification at sea level. They of course didn't state that it was at standard temperature pressure when this test was done, and I assume it wasn't done at standard temperature, but it was close enough that the ideal gas law should apply here, and thus, by extrapolation or whatever, I can use these P1V1 equations. So I really do think that the combustion chamber volume, as stated on LC Engineering, is for most of these engines 57 cubic centimeters. Even though that puts the compression ratio about 10.4 to 1, I have a feeling that combination of the shape of the piston and the shape of the combustion chamber and the way that the valves and the spark plugs sit in that head has quite a lot to do with the actual compression readings that you get. Because again, I'd be hoping for somewhere around this, and we're up there about 4,800, 5,000 feet above sea level. And then I'd be expecting this in a good running 22R. Not brand new, you know, not that 171 PSI value, but certainly would prefer this value to this value at sea level. I'll be curious in the next week when I pull the cylinder head off my 84 Toyota to measure the volume with a beaker, measure the volume of acetone it takes to fill the combustion chambers once I put a new set of valves in it. And then likewise, I will measure the amount of volume of acetone that it takes to fill the bore of the cylinder up with a piston in it at top dead center with the head off. Probably won't be able to do it with a head gasket on, so it won't be a completely accurate value, but those two combined should give a pretty good estimation of the actual volume of the combustion chamber at top dead center. Anyhow, hopefully if you're having questions about your readings, you can gain some insight from this. I will say, I think that the truck has a burnt valve on one of these two cylinders. I'm relatively sure it does, but I'm not, again, like I said, entirely trusting the results here that I got. By virtue of the tool I was using not being completely seated into the cylinder head. Really, you want them to be tight, otherwise you might have some pressure leakage, but no, we'll go ahead and do this again with the engine hot, and again, expect all of your results to be within 15% of each other, sort of, you know, or the lowest value to be at least 75% of your highest compression reading. If you kind of keep that in mind and know that all of your values are within a certain range, and again, you want to use one tool for all of this. You don't want to change tools through the middle of it, because even if the tool isn't accurate, you know, it's not hitting the bullseye every shot. If it's got a good grouping on one part of the target, that'll give you a good enough approximation of the internal health of the engine. Enough to lead you down the path of thinking, okay, should I do a leak down test on this? Does it got a blown head gasket on the first two cylinders or whatever? And then you can always test with a different apparatus, one that you know to be good, one that's calibrated to see the efficacy of your original piece of equipment. Anyhow, hope this helps. Best of luck.